Rationalizing the Denominator in 5 minutes. When you're dividing by an irrational number, it's important to remember what you can and cannot do. In the example on the left, both the numerator and denominator are both radicands. And radicands can perform operations with other radicands only. So we can divide square root of 6 by the square root of 2 to get the square root of 3. However, in the example on the right, the numerator has a radicand of 6, but the denominator is not. It's an integer. The square root of 6 cannot be divided by 2. Even though 6 is divisible by 2, the 6 is part of a radical expression. Therefore, they cannot be simplified. Sometimes, when you're given the square root of a fraction, even though it's one expression, the 4 divided by 9 might not be able to be simplified. But you're allowed to split the radicand into 2 separate radical expressions, giving us the square root of 4 in the numerator and the square root of 9 in the denominator. And since the square root of 4 is a perfect square, and so is the square root of 9, we can actually simplify this fraction now. The reverse is also true. If you're given a square root in the numerator and a square root in the denominator, and they're not perfect squares, you can combine them back into one giant radical expression with the fraction underneath, therefore allowing you to reduce the fraction. Once you've reduced the fraction, you're allowed to split it back into 2 separate radicands, allowing you to take a perfect square or leave one that isn't. Now we have a single fraction again, but only the numerator has a radical sign. And that's important to this lesson. The denominator is never allowed to finish when it still has a radical sign. Here's an example where that happens. 12 cannot be divided by 15, so if I join them back together as a single radicand, I can simplify 12/15 by dividing them both by 3. When I re-separate the fraction back out, I'll get the square root of 4 divided by the square root of 5. And the square root of 4 is perfect. That's where this 2 comes from. But the square root of 5 is not. So this expression is simplified as far as it can go. However, we're not allowed to stop there. If your denominator still has a radical sign, which means it's irrational, then you need to do something called rationalize the denominator. You need to rename this fraction so that the denominator no longer has that square root sign. The process of eliminating a square root sign is simple. The opposite of a square root is a square. So if I want to eliminate the square root of 5 from the denominator, I simply multiply the entire fraction by the square root of 5. In a sense, I am squaring the square root. Here's the work. If I rename the fraction by multiplying both the numerator and denominator by the square root of 5, then my denominator will become a perfect square. And when square rooted, the denominator will no longer be irrational. Unfortunately, it makes the numerator irrational, but that is allowed. So in order to rationalize the denominator, you simply multiply the numerator and denominator by the same value as whatever the denominator is to make it a perfect square. Let's try practicing examples where you don't need to rationalize the denominator and when you do. In example number 1, both the numerator and the denominator are perfect squares. That would leave us with the fraction 7/6. For question number 2, the numerator and denominator are not perfect squares, and if I combine them together to a single fraction, I can create a perfect square. For this third example, if I join the fractions back together here and reduce each, by dividing by 5, I'm going to get 9 over 16. I didn't start with perfect squares, but after some simplification, I got perfect squares. So the square root of 9 and the square root of 16 can be performed. In this example, these numbers cannot be put underneath one radical sign. And that's because the denominator contains a coefficient out front, which is not a radicand. In order for me to eliminate the square root of 3 in the denominator, all I have to do is rationalize it by multiplying both the denominator and the numerator by itself, the square root of 3. This will give me the square root of 252 in the numerator and 2 times the square root of 9 in the denominator. Now I can start simplifying my radicands. In the denominator, I'm going to get the square root of 9, which is 3. And eventually, that means my denominator will be just an integer. So now I have rationalized the denominator. All I have to do now is simplify the numerator. I'm going to go down my list of perfect squares and see if I can find any factors that divide evenly into 252. Use your calculator to check. I found that 36 times 7 will work. Well, the square root of 36 is perfect, but the square root of 7 is not. So the square root of 36 can be performed, and the square root of 7 will remain, leaving me with 6 square roots of 7. Now, in this fraction, the numerator has a coefficient and a radicand. The denominator has just a coefficient. Coefficients are allowed to do math with other coefficients, so we can actually divide 6 by 6 and leave the square root of 7 separate. And 6 divided by 6 is 1. The final answer here is the square root of 7. Let's try this one last time. The numerator here is 3 minus the square root of 8, which is allowed, but the denominator is the square root of 3, which is not allowed. We will rationalize the denominator by multiplying both the denominator and the entire numerator by the square root of 3. This will give me 3 square roots of 3 minus the square root of 24, all over the square root of 9. When I start to simplify here, this one will become a 3, and this will be 4 times 6. And 4 is a perfect square. So now I have 3 square roots of 3 minus 2 square roots of 6 all over 3. Now the first term has a coefficient, the second term has a coefficient, and the denominator also has a constant. These numbers can perform math with each other. So what we're going to do here is we're going to divide the coefficient 3 by 3 and this one by 3 if we can. Now, unfortunately, 3 can be divided by 3, but 2 cannot. And if one of the numbers cannot be divided, you're not allowed to do dividing at all. This is where we finish. And that concludes rationalizing the denominator.